Today we're going to do some examples of electrostatics problem solving. Say, for example, we have a metal sphere where we have induced a charge. If the metal sphere started off with a net charge of 0, that means it has the same number of protons as electrons. But if we added 1.2 times 10 to the 15 electrons, it would have a net negative charge. The question is, how many coulombs is that charge? This really is a dimensional analysis or unit analysis problem hiding as an electricity problem. We basically have to convert the known amount of electrons into the number of coulombs that we want. I start by writing what I know. It's 1.2 times 10 to the 15 electrons. And then I have to set up a conversion factor. So 1.6 times 10 to the negative 19 coulombs is equal to 1 electron. Notice that the electrons cancel out, leaving us with just coulombs. Multiplying this out, we get 0.00019 coulombs, or 1.9 times 10 to the minus 4 coulombs. Of course, these are electrons, so we have to remember the minus sign, because it's actually a negative charge left on the metal sphere. Let's try another problem. We have two more spheres, A and B. They happen to be 3 centimeters apart. Now, QA has a charge of plus 1.5 microcoulombs, and QB has a charge of negative 1.0 microcoulombs. What we want to know is what the electric force is between these two objects. Remember that the electric force is Coulomb's constant times the two charges divided by the distance between them. The numbers we have, so we have 9 times 10 to the 9 newtons times meters squared over Coulomb squared, which is Coulomb's constant, times 1.5 times 10 to the minus 6 coulombs, which is microcoulombs, and a minus 1.0 times 10 to the minus 6 coulombs, all divided by the radius. Now here's a word of warning. Most of these problems are in centimeters, but Coulomb's law is in meters, so you have to do a conversion. Otherwise, you're going to be off by quite a significant factor. You can always check if you put things in the right place and if your units are correct by canceling them out. So we have Coulomb squared and coulombs, they cancel. This meter happens to be squared, cancels out with that one, leaving us with just newtons, which is what we want. Plugging in the numbers, you get 15 newtons for the magnitude of the force. Since QA and QB are opposite signs, one being positive, one being negative, it is an attractive force. So sphere A feels a force of 15 newtons to the right, and sphere B, by Newton's third law, has the same force, 15 newtons, but to the left. Let's do another example. This time the spheres are 42 centimeters apart, and QA is a negative 8.1 times 10 to the negative 6. And QB is a negative 8.1 times 10 to the negative 6 coulombs. Notice they are both negative, so they're going to be repulsed from each other. So plugging into Coulomb's law to figure out the magnitude of the electric force, we have 9 times 10 to the 9 Newton meter squared over Coulomb squared times a negative 8.1 times 10 to the minus 6 coulombs times another negative 8.1 times 10 to the minus 6 coulombs, all divided by 0.42 meters squared. Notice I converted it to meters. Plugging in the numbers, you get, in the magnitude at least, 3.3 newtons. But since they're repulsing each other, the force on A is to the left of 3.3 newtons, and the force on B is to the right with 3.3 newtons.